want to present to you guys on maritime polar operations, and I want to accomplish a couple of things. Number one, I want to promote the Arctic as a maritime region relevant to the United States because it's on one of our corners. Two, I want to evoke some simple concepts that we've used to contend in high latitudes. They're all simple, but not necessarily easy or implicit. And I want to introduce a keyhole view for geopolitics and some implications that we might be seeing for the next couple of decades. Environmental standpoint, real quick, there's an ice cycle and there are forces that act on it. In this fall, so like November, December, ice starts to accumulate. First, it starts from grease ice, forms into first year thin ice, medium first year, and then to thick ice. Very easily in excess of 1 meter, that's first year ice. 2-3 meters, very easily achievable as well. Multi-year ice can exceed 12 meters and more if glacial, right? So the South Sea, Antarctica, if something calves, very big icebergs, don't want to touch it. Just like anything else on the water, wind, current, Coriolis, and geography of the region affect this floating ice, which is unpredictable and asymmetrical. Flows are sheets of ice that develop and they break up over the season. They accumulate and they turn into rubble, they refreeze, they get compacted against the shore. If it's shore fast ice, they break away again. And so there's a huge range of ice types that you see. Through my 7 voyages in the ice, every time I've seen new ice, and it was a new challenge. Maybe somebody with more experience, 30 or 40 years, maybe they get to see the same ice all over again. But as we know, the weather's also changing year to year, so there's that. Real quick, ice pressure builds from force-loaded flows across the season. Ridges create vertical development and ice pressure, and it can get really dynamic. One sea story real quick. We were 300 miles behind the ice edge north of Alaska, next to the Mackenzie River. And so sea ice freezes at 28 degrees Fahrenheit. That's salt water. Fresh water freezes at 32 degrees Fahrenheit. The seawater where we were was 28 degrees Fahrenheit, so the water column was ice. And all of a sudden at 2 a.m. on my watch, the ship is starting to lose power. And I'm thinking, did we have an ice strike on the propeller? Did one of our generators have a casualty? It didn't. No alarms are going off. Nothing's happening. It's like, what is happening? Then we check the salinity on the monitor because it's a scientific research vessel. We have all a huge amount of data, which is necessary. And you see the salinity had tanked down to the freshwater levels, but or brackish, and but the temperature of the water was still 28 degrees Fahrenheit. So virtually the entire water column beneath the ship was turning into a slurry and freezing up. So once we figured that out, we finished our operations, got out of there. Just one way that region or the presence of a freshwater outflow might affect your operations. Every single region, whether it's Alaska, Canadian, European, or if you're in fjords or with glaciers nearby or no glaciers, and world weather, the South Sea, for example, will change ice. There's no same region with ice. The Baltic ice will be different from the Great Lakes ice, will be different from the Arctic. I don't know if this video will work, but this is just an example of how dynamic it can be. Oh, very good. This is a radar image. This is us tucked in, and you can see all the ice with Coriolis moving on around us.
It's trying to devour you.
Oh yeah, it's a fun time. So you can't just bed down in a piece of ice for 6 hours or 4 hours or 1 hour and get back up and figure your situation is the same. A lot of situational awareness goes into this. It's taxing. Here's another video. I don't think we have audio, but it would help to have audio. It's not a problem though. This is us in. Whoa. Are you driving?
No, I'm trying to
Okay.
get volume.
It's a longer video than 2 seconds. I don't know. I'm frozen. Yeah. keep the audio on? Can we keep the audio on through the presentation? Cool. There's a couple more videos. So it's just wind. But here we are in just developing first year ice. This ship can break 1 meter at 1 knot at full power, and it's PC5. So we'll cover more of that later, what that means. Very good. Some limitations and high latitudes. All right. Are limitations of weather stations and forecasting, satellite coverage, and magnetic flux, interestingly enough, is vertical at the poles, not horizontal. So magnetic compasses do really weird things. And in the United States, we don't really have repair refuel facilities in our Arctic. Very good. This is Steve Roberts on his opinion, on his take. So sea ice isn't lake ice on a large scale. 1 satellite image per week, which is what we got, we'll go more into that in a little bit, is not enough. Sea ice is like the weather, changing fast. You must track it real time, but you don't have the data. It doesn't exist, so you make do with what we have. It's always a struggle. Ships that aren't ice capable don't belong up there. Only icebreakers have any business up there. 30 years. So navigation, there's some unique points how we do it. You saw the video. We need a guy like Steve Roberts, or that ship needs a guy like Steve Roberts to compile data on his GIS, which is a geographic datum map server. He compiles satellite imagery that's pre-planned for the ship based on the area of operations, wind, current, and all NEMA data over universal data port, and transmits it over the vessel. So, if you're on your phone, you'll plug into UDP and know exactly, if you're the captain in your stateroom, you'll know exactly where the ship is, what it's doing, the sea temperature around you, et cetera, et cetera. This includes the fiber optic gyro, GPS, water temp, air temperature, et cetera, et cetera. The ice crew then loads it all into his map server and makes it available to the nav team. It's like a Ectis on steroids. This requires a very competent nav team that is able to digest all this data and actually use it. Again, OODA loop, this is the observe and orient, gathering as much data and making it available and digestible to ourselves as possible. So with that satellite imagery, with that satellite imagery, this is an example of satellite imagery. We'll compare it to our micro scale up to 4 nautical mile ice radar, and some defining features is what we're looking for, again compared to DR. For example, there's this lead right here in this satellite imagery, and then you might have a lead that looks like this on the ice radar. Everybody's following along, great. This image of satellite imagery, it might render on the ship 16 hours late. So you saw how dynamic that radar image was over the course of 6 hours. This might all be rotated and different. So it requires the nav team to keep constant watch on what's been happening and where defining features, for example, like you might have one chunk of ice that you identify on 4 nautical mile scale, and try to go from there based on your past position, where you might be going. So that's navigation real quick. We talk about knowing your ship. So huge fundamental is knowing your vessel. There are 5 ice classes for polar class vessels, 7 technically, but only 5 that are really designed to be in the Arctic year-round. Part of this is understanding your ice ratings, hull framing, shell plating thickness and temper, also propulsion and power generation. And how you do that is by, we do it by studying technical drawings, which is very simple. But how many people on a ship are actually digesting technical drawings in their free time? Or looking up models of their ship. Here you can see that this vessel, which actually played a role into us getting nipped, has a very vertical sort of hip area versus all these compound curves up here, right? We actually did end up getting nipped, which just means that we were pinched between two flows for a time, and this was where we got nipped, exactly where we expected. But if you didn't think of it beforehand, then you might be surprised. Also, another sort of limitation to this vessel is that this flat area where it got nipped has a very short lever arm to the propulsion, right? Advanced Ship Handling 101, lever arm, vectors, etc. Technical drawings, here's an example. these are the motors aboard our vessel, well, aboard that vessel, Ivy Sekuliak. One, you can't read it here, but one of the technical specifications was that these motors are rated to 22.5 degrees roll periodic. It's an icebreaker. We've definitely done rolls over 47 degrees and regularly over 30 degrees. So you're outside the rating of the motors. Nature will have its way with you. You might as well know when you're outside your ratings or when you're inside your ratings. Doesn't mean you don't breach it if you have to, but it's good to know when it's happening. Here you have overload charts for the motors and how much they can be overloaded, which is 150%, and for how long without incurring damage. It's important. Ice loads on propeller are right here. You can easily impinge 110 to 250% of the normal water load onto an impeller by putting ice through it. So if you're at maximum kilowattage already and you hit a chunk of ice, all that equal and opposite actions, right? All that force will go back up into your propulsion system and exceed the ratings. This is pretty much what all that means, and we did it. We shattered our shaft liners, but it was okay in the end. We had awesome engineers on board. I don't know how they did it, but we ended up finishing the mission and doing repairs with a really good dive team in Seward. Some ice classes real quick. This is based on the Polar Code. PC1 through PC5, here's the description. I'm not going to go over it just for time. And then PC7 is not year-round, and their description would be summer, autumn, operation, and medium first-year ice. May include old ice inclusions, but they are not meant for year-round operations. Some of the classifications, some of the requirements that the DNV and other class societies are looking for are, main propulsion, machinery, steering, any auxiliary emergency system, internal watertight integrity, extra stability for ice accumulation, abrasion ratings for steel that your hull is made out of. That is above and beyond. You don't normally expect to abrade over the course of a ship's life, but with an icebreaker you do. Here's an excerpt straight from DNVGL. They have a really great online interactive system to look up exact specifications. This describes the compression forces that each PC polar class is rated for in meters of thickness of ice. So a PC1 rated vessel is supposed to withstand compression forces of 3 meters, versus a PC7 vessel is supposed to withstand compression forces of 0.5 meters. Big difference, and there's a reason there's distinct polar classes. There's some real PFM that goes into this, and some real engineering. Right here is an example of the formulas that go into just the shell plating thickness for bottom areas on a ship. That includes, and it's only for transverse framing, and corrosion and abrasion allowances. And that's just for 3 out of the 13 areas that they have to specifically design and take into account for a vessel that's polar class. Other considerations that go into polar class is having heated windows and not just clear views, specialized life rafts that are heated, Arctic immersion suits and survival kits in case you need to abandon ship onto the ice, specific design of exterior piping and machinery so they don't blow out and you're putting hydraulic fluid into the Arctic, which is pristine. Heated decks, redundant engineering systems, and very importantly, heat recovery, as well as the temp ratings, again, important. Just examples of how much goes into this. So long story short, you can't really retrofit a pre-existing ship to being ice capable or a feasible polar class. So we've talked about the external environment, the internal environment, and understanding specifications for the ship. Bridge resource management and leadership and management is a huge player in having a successful operation. If you don't know your environment, if you know your environment and you know your ship, but you can't relay the information appropriately or implement it to your crew, you're not doing much. You're dead in the water. So one way we did this was we implemented daily ice briefs, where we can bring it all back together. If we saw that last night we exceeded loads on a certain generator configuration, we would address it, in person and have a training moment. Another thing we would do, the intent of a daily ice brief was primarily to disseminate clear operational intent for the vessel for the next 24 hours, DR'd from the previous 24 hours data. That's everything: navigational, satellite, engineering data, etc. Where the captain could relay this intent to the crew and compare it to the ice crew or Steve Roberts information that came in on the ice development over the past 24 hours, what we've seen, as well as the bridge team's observations over the past 24 hours, what tactics worked, what didn't work, what kind of ice did they see. And it's a bit of a two-way street to kind of tell the captains, like, hey, this is not really feasible. We've made one knot of progress over the last 6 hours, and we need to make 4 knots to accomplish this objective. We're not going to make it. So kind of come back in and pow out every 24 hours and have a two-way street with that. You rinse and repeat, and you carry a notebook and record religiously. Very important. So this is just, again, that OODA loop, just repeating it and seeing where are we in this loop. Most importantly, you go where the ice allows you to go. You don't impose your will on something with that much force. One sacred rule, try to keep it under time here. One sacred rule is slow down. That's both yourself and the ship. One thing to note is 4 knot speed made good is very good ice breaking, at least on this ship and what we were in. There's a video I have to offer from left to right. You'll see the ice radar gyro on the center line, along with on the overhead, you'll see satellite imagery. The generators you'll see at 2,500 kilowatts each, and the wind's 20 knots in this video. So here's our gyro, here's the ice radar, and here you'll have the satellite imagery that's always up. So you're always checking back and forth where you're at. That's the anemometer on the starboard side. And here you can see one big generator and one small generator, which is a total of 2,500 kilowatts. And so it's taking 2,500 kilowatts to break through this ice, which is all very homogeneous and flat. This is the nicest ice breaking you could possibly get. Yellow lights to offer contrast against the albedo of the ice, so it doesn't tax the bridge team as much, and you can get a depth perception for it. We didn't start with yellow lights. That was a rough trip. All right, moving on. Number 2, having slowed down, you just buy yourself time to think critically and exercise patience. So that's very important. In this next video, it's a very conscious decision to stop, slow down, think critically, and allow yourself time to let it soak, whatever you're doing, and think before you do. And that's very intuitive, and it's easy to say in a conference room, but when the ship is vibrating and you need to go somewhere and somebody's hurt or whatever else is going on, or you're tired or you're stressed out, it can very easily get away from you. Or ourselves, I should say. This is another example of only going where the ice is allowing you to go. Here, the ship is stopped relative to the ice, and you can see we're just letting this wash. Oh, I messed it up. How do we do? Can you? Yeah, thank you. And we're letting this wash break up the ice slowly. I'm not kidding about slowing down. 5 minutes, set the throttles, let it wash, get out, get a cup of coffee, mostly that's how I did it, to manage myself so I didn't get impatient and touch it, right? One nice thing about this vessel was that she's extremely directionally unstable because she tapers down like a tadpole, and so that makes her highly maneuverable. And along the sides, you also have ice reamers. So in a situation like this, right here is the ice reamer, and where our wash is degrading the ice, you actually have a little bit of wiggle room, about 3 feet on either side, to allow yourself to wedge into the ice and act on it in a different way and herringbone stitch it. We're going to skip this because it gets down into the nitty-gritty tactics, and we don't have time for that. Here's another video. You can kind of see how we're selecting our path, staying perpendicular to these pressure ridges. The white signifies something I call popcorn, or like aerated ice or rubble fields. And you can see these flat, smooth, dark patches are flat, homogeneous pieces of ice that allow the nicest ice breaking. So we're choosing where we go. We're not freely going wherever we want, especially on a PC5. These next items are skipped for brevity. Yes, 5 minutes. Good. But the key takeaway is that there's a lot of skills and tactics that take a lot of time to accumulate, including for myself. I'm nowhere near where I would like to be. And they're always under development. I've never had a watch that I got off the bridge and said, yeah, I did a really good job. It's like, if you survived, it was good. So the following slides are tactics that we skipped. On the side are descriptions and considerations for the navigator that normally I would take a week or two to go through, but we're not doing that here. Routing via ice radar, working with the ice as opposed to against it, transiting flows under pressure, long distance routing and utilizing radar and satellite images, routing in open water with flow bergs, exiting an existing channel, transiting an existing channel, heaving to in a flow with an expected wind shift, and rafting in for storm force winds. Entry into the ice, even this small, requires extra thought and precision. Ice stations, if you're getting people onto the ice, requires some thought, no-go and no-go zones, and weather. You have your isobaric lines, and then there's like a 30-degree offset to true wind when that is exhibited, and then from the true wind there's also another 20-degree offset with ice drift, depending on how much superstructure above the water that ice has. So I hope you guys pay attention. Well, you guys do, but this is for other people. You need to pay attention to meteorology. Freezing spray obviously is a big one, and then even something such as simple as ice blink and water sky, which goes back to the heroic era and indigenous people. This is what they taught contemporary navigators. It's like, here's an example of ice blink where the albedo off the ice is reflecting into the sky, and here's an example of water sky where it's not. Quick, I want to zoom out in the regulation and just kind of shotgun blast you. The IMO Polar Code governs maritime shipping in the Arctic, and it's supposed to promote safe ship operations and the protection of a polar environment, not addressed by other IMO instruments. And they do that through a Polar Water Operating Manual, which any ship that's going to operate in the Arctic and be compliant with it needs, which is a bit of an addendum to the SMS, and it includes things like standing orders for the ice, specialized garbage and waste food disposal policy, contingency planning, and what happens if this happens? What's the next step? So being in line with that, and here are some familiar infograms that everybody's kind of familiar with from the IMO that you might see. But my open-ended question is, who will enforce it in the Arctic? Polar bears, exactly. So I will read this off just because I'd like to. The geopolitics of the area are interesting. Here you have the Arctic, and you have the Northwest Passage from the United States across the North of Canada. Here's the Northern Sea Route. Here's another route across the pole, the transpolar route, and then this European thing. But anyways, moving on. United States, we have 2 icebreakers that are operational. One is being built for $1 billion, and from what I've read in the Indo-Pacific DoD Arctic Strategy Journal, one stopgap that we're using is that most of our advanced fighters are in Alaska, because we don't have icebreakers. There's plans to build a deep water port in Nome, Alaska, which is like right here on the south side, which is still on the south side of the Alaskan Peninsula. There's limited infrastructure for repair and refueling in the United States on the north side. The region's resources include protein and fossil fuels in our waters, and it's the only USA border not buffered by an ally or foreign diplomacy, which has been kind of the U.S. policy since the Marshall Plan. In April 2023, just now, there was a Senate DoD budget hearing, and Chief Naval Officer Mike Gilday, who's in charge of the Navy, his response to questions on U.S. Navy's plans for Arctic presence was that there is no requirement for the Navy to have icebreakers. We never have had that requirement, and that is the article in Capt, if you guys I'm sure you guys know that. Russia, half of the Arctic is bordered on Russia-Siberian coastline, and they consider it their front door. This is self-proclaimed. 20% of their GDP stems from the Arctic. They have 44 icebreakers operational, 16 on the way, and their fleet includes nuclear-powered vessels. They have extensive investment in infrastructure and 6+ shore facilities along the Siberian coastline, and their northern fleet is stationed there, and it hasn't moved during the Ukraine. That's to protect the northern sea route, which is projected to open up years before the Northwest Passage. As far as China goes, they have been historically inclined to territorial disputes. They have a lot of them. And they claim to be a near Arctic state, presumably for influencing policy, which they are doing. They engage in debt diplomacy, for example, Greenland, Russia, and global infrastructure loans and investment. And any assets of theirs are state-owned because that's just the way things are, i.e. Antarctic stations. Their interests include trade routes, regional presence, and Arctic protein. And in this DoD Journal for Indo-Pacific Affairs on Arctic Strategy, the PRC is projected to economize 60 to 120 billion US dollars in cost savings per year by using the Northern Sea Route over the Panama Canal to trade with Europe. The PRC also has 6 Navy-Army icebreakers specifically for the Navy and Army. And they have multiple commercial scientific icebreakers. Our Navy doesn't have any. As far as Norway, Europe, and Canada go, the Norwegians, Northern Europeans, and Canadians have been in the Arctic since the heroic era, and Canada exercises the most presence in the Arctic North America by far. I want to end with the Arctic. Lower latitude disputes, for example, Ukraine, have and will influence Arctic regions moving forward. For example, discussions at the Arctic Ice Convention have ceased since Ukraine started. I think I misspoke on that one, but some talks have stopped because of Ukraine. But a typical voyage for this ship, I believe the endurance is 59 days, and there is a day rate for it. So a lot of that depends on National Science Foundation's budget and the proposal from the PI or chief scientist on board. So this ship can do up to 59 days. We've had some that are like 14 days, and honestly, even like 12 days in ice, you get out of it and you're like, that's the longest 12 days you've ever sailed. I mean, at least that was my experience, and I loved it. Don't get me wrong, Type 2 fun all the way through. If that